Now, as you can imagine, the 1,3 axial strain is related to the size of the actual thing at the axial position, right? So the stability of these two conformations that I've illustrated here, so if I go and I take these two, that got really drawn all over, but if I take the consideration of two different configurations, all right, so I do an axial configuration here where I've got the CH3, and then of course in every third position I have the other axial thing, and then there's some sort of equilibrium chair flip that wants to drive it over to the next configuration. And you'll notice how I'm drawing my chair after I do my chair flip. I'm drawing it now the other way, all right? And now my chair tells me that I've got this now in an equatorial position, and the former axial hydrogens are also in equatorial positions. All right, I could probably do just a wee bit better on that one. Make that look a little bit more that way. Okay, so there's very little impetus for it to go back. So when we draw our equilibrium arrows, of course, we show that there is this driving force that likes to keep it pushing this way, and what we see is that this is more stable by 1.7 kcal per mole. So if 3 kcals per mole, like we saw in the rotation, if ethane happens at room temperature, you can bet good amount of money that this happens, this flippity floppity flippity happens without reservation over time at room temperature too. There's by no means locking it into any configuration. Now, that's for methyl cyclohexane. You can get fairly large substituents, of course. So if instead of methyl cyclohexane, you have, say, T-butyl cyclohexane, right? So now that T-butyl, that's all over the place. You've got sterics coming out of your wazoo. So now there's going to be a huge drive and actually almost no impetus for it to try to get away, because, again, in the equatorial position, once you've got this fitted down here where it can do little harm to anybody, and you've replaced the equatorial hydrogens now. So now all you've got are equatorial hydrogens that are bumping into each other, and that's not bad. Whereas the sterics up here are just ridiculous. Then you have you're much better off. So in this particular case now, you have hit 5 kcal per mole. All right, so you can see that it goes up pretty quickly, and that's for the simple things about as high as you can go. Now, what if you had to choose, right? What if you had to choose? So T-butyl is conspicuously larger than methyl, but let's say you had what they'd call a Hobson's choice, right? So you have this, right? You got T-butyl up here, and then you've got, if I draw it in 3 dimensions, I'm going to give it away, aren't I? So let's not draw it in 3 dimensions. Let's draw it in 2 dimensions first. All right, so now we've got a cyclohexane here, and now we've got a CH3, and we got a T-butyl. So now what do we do? All right, what do we do for this compound? Which one do we have to put up, right? So we have to draw one of 2 configurations. So the CH3 and the T-butyl group, I've not actually drawn anything, any shading, but let's just say they're both on the same side of the ring. Oh, let's draw that again. All right. They're both on the same side of the ring. They are what you would call cis to each other on the ring. Now keep in mind, cis and trans are not equatorial and axial. All right, cis and trans in this context means they're cis on a ring. So if you draw what a cis on a ring means, it almost certainly doesn't mean they're both axial. In fact, they could be in this particular case, but they could both be equatorial, right? So if I draw these cis on a ring, and I draw this one in an equatorial position here, then I go 2 down, and then this has to be an equatorial position as well. Let's just keep it CH3, which means that these hydrogens are also axial. So these are both like that, they're both facing down and they're both equatorial, but this is cis. This is a cis arrangement, all right? Now, what happens if I made one of these trans? Okay, if I made one of these trans, now what do I do? Because now I actually have to make a choice, because if one is trans and one is cis, in fact, let me draw another one so that these notes don't get terribly confusing. If I draw one that is trans, if I draw a cyclohexane that is trans, now I have to make a choice, because now I can draw a configuration where the T-butyl is going to be axial, right? And if it's trans, then that goes there. And this has to be on the opposite side of the ring, which means that has to be equatorial facing down. Because that goes up, that goes, oh. So now I have to make a choice, right? So let me just draw this, right? So if this is equatorial, the T-butyl group is equatorial, then I've got an axial hydrogen, right? If that goes straight up, equatorial, then on carbon 2, I've got something that goes straight down, and on carbon 3, I got a hydrogen that goes straight up. In order for this T-butyl group to be cis from the methyl group, that means this methyl, that was beautiful, then this methyl group must actually be equatorial. Okay, right? So convince yourself of that. If I draw the T-butyl group axial, then I draw that's axial, that's axial, that's axial, right? But I notice they are trans from each other. In a trans configuration, that means that if this is axial, that has to be equatorial, and vice versa, right? And the problem with this configuration, of course, is you got a T-butyl group, and a T-butyl group is 5 kilocalories per mole. So that's going to be short-lived, because it will want to preferentially go to the lower energy one, and the lower energy one is just the methyl cyclohexane in the A strain configuration, right? So it's making a choice, an energetic choice. Again, I'm personifying these things, but what can you do? It's making some sort of energetic choice where it's going to put the T-butyl group, I'll just put that here. Now the T-butyl group, so now we do that's axial, and that's axial, and then to make sure that's trans now, that's our CH3. All right, so now I have this trans configuration where instead of the big group, the small group is there. So the takeaway is, you know, put the smallest substituents in the axial configuration. Put the smallest substituents as possible, because sometimes it's not possible to have just a bunch of hydrogens, right? So, you know, what happens if you've got 3 configurations? So let's say you got 3. Let's do another practice problem here. All right, and I'm going to make it so that you got 2 methyl groups, and they are cis to each other. They're on the same side. And now you got an ethyl group, right? So an ethyl group has a, if we just look at it strictly in, let's see, a methyl group is about 1.5 kilojoules, an ethyl group That's actually not too different. Let's go with it's just so clear. It's just so clear when you do the t-butyl group, right? So let's go with the ethyl group. The ethyl group is obviously you've got to make a decision here, right? Because you can draw two different configurations. One in which we'll start counting with the methyl, and it doesn't seem like it matters which one you go, because it's this is methyl, so it's 2-ethyl 1,3-dimethyl, right? Cyclohexane, and these are going to be on the same side. So let's first just draw these in the chair. So these are now this is the chair configuration. I've decided arbitrarily to make both methyls axial, and now I've got this ethyl group that's cis to both of them, and I'm sorry, that's trans to both of them. So the two methyl groups are both cis to each other, and then this one's trans. So that's CH2, CH3. All right. So that makes sense. All right, and if we just look at the 1,3-A strain, we notice they're bumping into each other. These methyl groups are bumping into each other, and down here you have essentially also methyl groups bumping into each other. This is like the least favorable way to write out these configurations, right? So this is going to be strongly preferring a ring flip to put everything into the axial configuration. And when we do that, that CH3 goes there, and because now we have a axial hydrogen here, an axial hydrogen here, and an axial hydrogen here. So it means that our axial hydrogen here, we now have this in a configuration that has, so see that this is now still trans to each other, because this is sort of axial up and that is axial down. And then the methyl group over here is all right, so then we're going to do the ring flip. All right, and so when we do the ring flip now, instead of the methyl groups being axial, the hydrogens will be axial, so we're going to draw these. So now those are definitely axial. And the methyl groups are still going to be cis to each other. So that's going to be axial. And it's going to be axial, pointing downwards. It's axial pointing, sorry, it's equatorial pointing downwards. This is equatorial pointing downwards, which means that in order for this to be trans to everything, it's got to be equatorial pointing upwards. So there you go. Now you notice these two are still trans to each other, and they're both equatorial. So clearly it has nothing to do with each other. Now let's consider, so last example, what would happen if we drew this so that you had CH3, CH, CH3, so the ethyl there, and the CH3 here, right? So this becomes a little bit stickier because now they're all cis to each other. So when they're all cis to each other, that means that one is going to be facing up in an axial position, and one is going to be facing up in an equatorial position, and one is going to be facing, so let's see here, up in an axial position. All right, and then you got hydrogen there, right? Okay, well, this seems a little bit, and if you look at the hydrogens on the bottom, like those are pretty sweet. That's just a bunch of hydrogens. Well, you got a methyl-methyl interaction here, so that's going to cost you. And you got methyl, so you've got these 1,3-A strains. Essentially, you can sum them up usually in what's called A values, and you add them up, And qualitatively, because we're going through this and you can look through your book, two methyl groups bumping into each other is way worse than an ethyl group bumping into hydrogens, right? So if you can get these two methyl groups to stop hitting each other, all right, it's like separating the kids, that would be fantastic, right? Because your alternative in this configuration is to, let's move back, feller over there, is to get the ethyl group up. And actually, the ethyl group is not so bad, and as you might think, and I'll show you why in just a second. The ethyl group is not significantly worse than a methyl group in terms of how sterically encumbering it is, because now if I draw this, now my methyl groups are equatorial, right? Because I've just done a chair flip, and they're equatorial in the same direction. They're both equatorial down. Now my ethyl group is just like straight up axial. Okay, but of course, there's axial hydrogen here. Just kidding. There's no axial hydrogen there because it goes up and then up, and then there's an axial hydrogen here, right? So there's axial hydrogens there, and then I can kind of draw that this is an ethyl. So right, there's a hydrogen coming out here and a hydrogen going out here. If I just point this methyl group over here, right, it's this big spinach is actually sterically away from these two hydrogens. So while I basically have some bumping of this methyl, what's called a methylene. So methylene is essentially CH2. So this group bumps into this one. You know, if this were a hydrogen right here, how much energy would I save? Not a whole lot, because I can just, this has rotation. So I can just move anything big out of the way, and that sort of makes it better. So honestly, now I've gotten rid of two methyl groups. I've gotten an interaction of two methyl groups. Those are gone. So these are now actually in much better position. I've replaced it with one ethyl group. And I told you one ethyl group is not much different than one methyl group. So essentially, when you're doing ring flips, try to get the least, if you have to put a substituent into an axial position, make it the smallest one. So that was a pretty comprehensive dive into essentially what we were calling Chapter 3 as a review. And just to briefly summarize about where you probably should be, we've focused a lot on looking at naming, so nomenclature. So nomenclature was a pretty big deal, and we looked at the different ways of naming things. You know, for nomenclature, you had your alkane roots, which were the ethyl, pethyl, propyl, all that sort of stuff. Kind of discuss the origins of the naming of the alkanes. And so you now know about the meth, the eth, the prop, and the bute, right? And they become adjectives in a way when you stick them onto the roots. And, you know, the root of these words depends on the length of the chain. So, you know, your nomenclature from your alkane roots, that, of course, depends on length of chain. All right, and so you learned about some substitution patterns and of common names. And the common names are what we're going to also emphasize here in this course, and naming priorities. That includes naming priorities as in like alphabetical, you know, you got to kind of keep them straight. The alphabetical priorities, the numerical, and that's to say keeping the number substitution pattern down on the numerical priorities and the alphabetical priorities. So there's a number of different things that you want to keep in mind. And then we also did the cyclo and I think it's called a bicyclo, but multiple rings. We covered both of those as well. And then in the second half, we really tackled conformations. Conformations, we call them conformers, conformational isomers, I'm not a particularly big fan of that. Conformational isomers. And in order to do that, we had to learn a new drawing technique. We learned Newman projections. And we learned about, of course, the staggered and eclipsed, which we already knew a little bit from I can't read and write at the same time right now, which we already knew about. We got from ethane's rotation, propane, and then, of course, the more complicated butane cycling. So we learned about the rotational dynamics and energy landscape of ethane, which we remember was pretty simple, propane, which was not much more difficult than ethane, and then we got to butane, and it did get a little bit more involved, but not honestly so much. And then, of course, we broke into the conformational dynamics of cyclic system. And really, I mean, conformational dynamics of cyclic systems as in cyclohexane for the most part. We did cover smaller rings. And we didn't really talk about why cycloheptane actually had a higher energy than cyclohexane. And you can probably do that yourself. I just remembered that I didn't. But the issue is that if you build a model, you can never relax all the strain. You will always have some amount of eclipsing, and you'll never be able to get 109 degrees without some eclipsing in the larger rings. So oddly enough, larger rings don't impart any real stability over cyclohexane. You have to get to some ridiculously large rings that basically start to act like straight chain alkanes. But what you did discover is that cyclohexane really is pretty idyllic in its ability to stay stable, but we realized that that stability comes with a price, and that is that it's all it's a terrible chair. So it's a price is that essentially you have to keep the A interactions, the axial interactions down. So we learned about axial interactions and how to minimize those, and the things that bump into each other. I mentioned it once, but I didn't really drive into it. The A values. And those are the thermodynamic values that sort of dictate who wants to have to bump into each other. And of course, in this process of flipping things over, we learned about the chair configuration, we learned about the boat configuration, and the weird little metastable state, or the weird little slightly more stable state that goes between the chair to the boat, which is the twist boat. That's always sort of fun to draw like that. The twist boat is a component along the path toward eventually getting to your lower energy the twist boat is on its way to the boat, and then that boat will go through another twist boat on its way to finally flipping over. And that those chair flips are important in order to get the axial crap, or the things that are touching each other in the axial position in an equatorial position, well, there will be much more friendly. And so that is the conclusion.